All right. Okay, I think we're gonna get started in just a minute here. Okay, so we're gonna go ahead and get started. So most of this afternoon is, the first part of this afternoon is going to be CESM3 development overview and component status. And then I presented this morning. So we're together from about now until 3 p.m. and then there's a break. And then at 3:15, the Polar Climate Working Group is going to meet in the Damon Room. So at the end, at 3 p.m., when it's break time, if you don't know where the Damon Room is, find me or Dave and we will show you where to go. Otherwise, if you're Ocean Model Working Group, you're gonna stay in this room. So you don't have to go find anywhere else. And that's when we start splitting. And then at 4:30 p.m., there's an optional self-pay gathering at Southern Sun. Bring cash if you're gonna come. Southern Sun is down the hill. Again, if you don't know where that is, come find me or Dave or Gustavo or Ian. Before we start the component overview, we're gonna have a presentation, kind of an ad for a June workshop cross-working group session that Diamond Takara is gonna present. I don't know that she's here yet, but I also wanted to say I already introduced myself to everyone this morning. Ian is here now, so do you wanna stand up and at least wave to people, Ian? In case you don't know Ian, this is Ian. He's one of the Ocean Model Working Group co-chairs, and then Gustavo, who already waved his hand. And Ed should be joining us online, and he's the other co-chair for the Polar Climate Working Group. Do we have Diamond online? I had a thing before, but I don't see it now.
Just one quick thing. Southern Sun does have an ATM.
Oh,
so
thanks.
You can get cash there too if you don't have cash.
I don't see Diamond online yet. Well, I guess it's 1 minute away, but cancel, sorry. I'll share this, and if Diamond comes, then she can add some context to this. But so in June at the big CESM workshop, there's going to be a cross-working group session about storytelling to craft climate science tools for communities. And this is put together by Laura Landrum, who many of you guys probably know, Mari Tai, Diamond, and then James Doney. Is that how you pronounce his last name? Doney. So Doan, okay. It is, yep, you could just say done, I'm sorry. So we would encourage people to be part of that if they're interested. Go ahead.
Diamond's face was on the
Oh, she was for a second?
slideshow. You see?
No.
Right there. You see? Yeah, but you can just look at yours in. That's true.
I guess, Diamond, if you're able to share your screen with this, let me know. Otherwise, I can share. I'm just not seeing her on the list of
She might.
people in the room. And I see that she is looking, has it open, but she's not in the meeting at the moment. So maybe what makes sense, I'll start with just kind of where CESM is in general. We'll check in if she's here before we get into the polar sea ice status, and then we'll do that, and I bet she'll be here by then, and then we'll do that, and then the ocean model status. So without further ado, oh, sorry. Okay, so CSM3 development and overview and component status. So some of this you guys will probably be like, oh, we already know this. Why are you telling us this again? So the first thing we wanted to announce, just so everyone is aware, we are still planning on a CESM tutorial this summer. The application is up right now, and the deadline is next Tuesday, February, or not next Tuesday, the Tuesday after that, February 17th. So if you or your students or postdocs or whoever is interested, please apply. There's no cost to attend, and we are hoping that there will be travel support available. I think there's a lot of uncertainty around that right now. So if in doubt, I would say apply. and then ask us, and Elizabeth Faircloth will organize that, and she'll have a lot more information. All right, so CESM3 overview. This is from Dave Lawrence, just some overview slides. So there have been significant updates to all of the component models in CESM3. Obviously, you're here because you're probably interested in sea ice or ocean parts, but you can see surface waves as part of this here as well. And then big changes to the land ice, the land, and the atmosphere. And if you want the full list, this will be posted of what the changes are and why. There's information here with links. If any of you are interested, we just want to make sure everyone's aware of this. On GitHub, there's a development run database, and we track all of the development simulations. So again, you can click this link when you get the slides, and this is kind of what the GitHub page looks like. And they have information in here about the simulations, what's different about them, links to the case directories, links to diagnostics if we have those, and any other discussion. And what that looks like is if you click on issues, that is about a single simulation. So when we talk about 271 later or something like that, that's case number 271. If you click on here, you can go look at what that is about. And then there's a discussion if there's a bigger issue. So you'll learn about the Antarctic circumpolar current. There's a discussion about what's going on with that under the discussions. And then the timeline. So this is, a while ago. CESM2 release was in June 2018. It was an 8-year development timeline, and we had 299 configurations. And we are almost there, and we're pretty close to this, where we have been working on this since 2018. And I think it really will be released soon, and we have just over 300 configurations. So I think we really are almost there. The target release date is June of this year. I think we are likely to, what Dave Lawrence said is we're likely to have some pre-industrial control simulations by the June meeting. I don't know that they'll be done. Just so everyone's aware, we are planning to do the CMIP7 DEX simulation still. We haven't been told that we can't, and we feel like this is important for validating and showing that our model is skillful and reasonable. So that's what these simulations are with the deck. So like I said, it's necessary for model validation and assessment. We are planning to do some other simulations if we have sufficient resources to do so, some of the other MIPS maybe, but we haven't decided which MIPS, which scenarios, all of that, and we would welcome your input during the discussion if you have strong feelings about, a different scenario you want or something like that, and it will all be resource dependent, of course. I don't know why that came back in later. And then some of the things you'll learn about today, things that have been slowing us down, because you probably thought, well, it's been several years. There have been challenges with the ENSO. I didn't add as a bullet point. There's been challenges with the Amazon and that it's too dry. And I think all the plants die, so that's a tree falling on someone. The Labrador sea freeze has continued to be a challenge, though I think we may have a permanent solution that we'll talk about, or hopefully permanent solution. And then most recently, we've been running into some challenges with the Antarctic circumpolar current, or the ACC, that the ocean model folks are going to talk about. So we're working on these actively, but I think we're kind of whittled down to some of the last few things that we need to address. And then there was a atmospheric model working group talk by Isla this Monday, if you wanted to look at that, about ENSO. We're going to talk about the lab sea freeze, and the ocean model group's going to talk about the ACC. So let me check if Diamond is online now. Do you see her online at all? No, okay. I guess given that we don't have the presenter for this, I'm gonna just say that since I'm not one of the people putting together this cross-working group, look out for more information about this cross-working group session about storytelling. And part of the point is to better communicate our science to different communities, make it more accessible, stuff like that. If Diamond comes back later, maybe we can hop off and talk about this. But in the meantime, I think we'll talk a little bit about the sea ice model and where it's at, and then we'll go to the ocean model. Okay. All right, so the sea ice model status. So again, some of this stuff you've probably heard before. What's new in SICE in CESM3? So the two big things are the flow size distribution. And if you were here this morning, you heard all about flows and sea ice and waves in the ocean. But we also have a new melt pond parameterization that's one of the more significant changes. The biggest challenge I would say has been, we had some challenges with the flow size distribution and cost, but the Lab C was one of the other challenges that we think we have hopefully solved. And what we're gonna show here are two simulations. So like development run 271 and 287, which are some of the 271's the longest run we have right now that has known issues, that has a pretty close to final-ish configuration. And 287 is one of the test runs with some changes in the ocean. And the diagnostics, you can look at these if you look at this, if you click this link when you get the slides. And one thing we wanted to mention is these are part of the Cupid package. And we're interested in if people want to add diagnostics to this, we're happy to work with folks to get those included. I think Marika mentioned this earlier, like maybe marginal ice zone area is something that we'd want to include in the future. All right, so here's our timeline. In CESM3, right now we have this flow size distribution, or the FSD. We have the sea level melt ponds. David Clemensoul, who is somewhere in the room, you moved slightly, so I didn't know where to find you. He primarily led development of that. And then we have some advanced snow physics, but I want to emphasize we don't have all of that on. We only have the wind redistribution component of these snow physics on. So all of these are in the fully coupled system as default. So if you run it, they'll all be on. So I would say the CSM3 code is mostly frozen. It's just model tuning and finalization and like dealing with issues that's ongoing. There's no major other things going into it. And we're hoping to have these pre-industrial runs by June, or at least started by then. And then what Polar Climate Working Group's thinking of for beyond CSM3, you've probably heard, again, some of these before, but landfast ice with a sub-grid scale bathymetry. We have parts of this in, but we didn't have it fully working by the time the code freeze happened. A size 6 MOM6 coupling on the sea grid. Again, I've done some work on this, ran into some issues, decided to put more energy towards getting the flow size distribution in the model. We're getting some improvements to ice conduction that will be in a later version of CESM3, as well as congelation growth. On the wish list, feels like perpetually, we have sea ice biogeochemistry. So that top group is like very likely to be in a relatively soon release of CESM3. Sea ice biogeochemistry, I had been recommended for funding for this from NOAA, but now that funding is on perpetual uncertainty. So maybe it'll come through, maybe not, but we really would like to get the sea ice biogeochemistry coupled with the marine biogeochemistry, and maybe do some other polar improvements to it. And then ice radiative transfer. And then things that have kind of popped up in the last years is things many people are interested in is working on machine learning and some of the machine learning parameterizations that'll go into a machine learning enabled version of CESM3, specifically with the flow size distribution, though if other people have other machine learning things they're doing, we'd love to hear about that. And then interest in regional ice ocean wave modeling. All right, so this is part of the regional ice ocean wave modeling. There was a workshop back in October. Dave Bailey attended, some of the other people in this room attended, and people were successful at setting up some of these regional grids with sea ice. And, but I think there's still some ongoing questions like how you deal with boundaries, how you deal with waves that's not in the regional models, potentially biogeochemistry. So there's lots that we're interested in. And in the morning session, Dan brought up, you know, there's likely to be another workshop, and many of the people here said they were interested in attending one of these crocodile workshops that might focus more on polar things, or there would be a big group of us from polar that would attend. So just pointing that out, if you're interested in this or you want to be involved in the development, we're excited to have you. All right, so just a little bit about the FSD. We heard about this all morning, but some of the people have changed in and out. So in CESM2, what we had was a constant flow diameter of 300 meters. The ocean waves were not damped at all by sea ice, and the ocean mixing was not impacted by waves or anything like that. In CESM3, we now have a prognostic joint flow size and ice thickness distribution. So you can see in this schematic, the flow sizes are different. There's also ice thicknesses within there. And the waves, the ocean waves are damped by sea ice, so this will damp the waves, and then it will impact ocean mixing below the sea ice. So we do have one-way coupling to the ocean. If you were here, Aaron talks about coupling to the atmosphere. We don't have anything like that with waves. And this is really important when we get to the Lab C situation, because what happens is when the waves break the sea ice, we get more lateral melt, which can lead to more open water, which can lead to more waves in some of these areas. And that's really what helped us, we think, deal with the Lab C freezing over issues. The second main parameterization we're going to highlight is the sea level melt ponds. As I said, talk to David if you want all of the details, but I just tried to summarize it here. So in CESM2, we had level ponds. The ponds, IPO ponds sit on top of the sea ice. They are sit, whatever. The area and depth grow by fixed ratio, but when they drain, it only reduces depth. So we had way too extensive melt ponds. This kind of nicely canceled itself out in that we ended up getting a really good albedo because we had compensating biases, but the melt ponds were too extensive and too shallow. David's done a lot with these sea level ponds where we actually account for sea level. When they drain, you reduce both depth and area. And this is based on the elevation above sea level, which is the hypsometry. And I'm going to point you to David for any other questions you have about it for lack of time here. All right, so S, probably many of you know, the Labrador Sea freeze has been a long time challenge in CESM. And so this is back from CESM2. I actually remember some of this vividly because I had my second daughter. It was like, everything's fixed. And then the last run I looked at before she was born, it froze over again. And I was like, not my problem. I came back, it was still a problem. Where you have that box right there, that's showing the Labrador Sea. We get ice that grows out far, too far south and east. And these are cute things. This is a slide I got from Cecile. So Cecile is saying we're trying to figure out how to drag the CESM boat over this ice. So this issue has come up over time in CESM and it reemerged in CESM3. So the problem was basically related to too much fresh water in the Labrador Sea. The thing that was really challenging about it, as you can see from this plot, is sometimes the Lab Sea froze. That's what happens when these ice fractions jump up. It would happen right away, but other times it happened after like 200 years. So you'd think you were good and then you weren't. So it was really unpredictable. The Lab Sea would freeze in like 30% of the runs, but in the other 70%, it was like, well, it's not frozen yet, but who knows what's gonna happen. And once it got frozen, it would stay frozen. And the thing that seemed to really, the two things that kind of impact this that we've used to address it are, first, we turned on the flow size distribution, and that has to be fully coupled. So we're not just passing wave information, ice information to the waves, but that the flows actually evolve over time. And we have turned off the Bodner ocean parameterization in the Lab Sea, and I'll try to explain that. And if you're an oceanographer, I'm sorry if I don't get that right. But this was, I think, the first case 247 where I think on a hunch, Dave kept the simulation running and it froze and then it unfroze. And we were like, well, is this like a weird one-off? And nope, in fact, this is what happens consistently in these simulations where we have the flow size distribution on. So the Lab Sea will freeze and then you break up, the waves break up the ice and you get that feedback starting, and then it seems that that is able to lead to an unfreeze of the situation. Unfortunately, we can't turn Bodner on. That is not a solution. So here's the feedback I just explained. That is how we are dealing with the Lab Sea. But for Bodner, so what Bodner does, it's a mixed layer eddy scheme. It basically deals with restratifying the ocean mixed layer, and it opposes deep mixing or convection, which is something that happens in the Lab Sea. And when the mixed layer depths get really big, restratification increases. So when this was on in the Lab Sea, it would basically restratify the Lab Sea. That would suppress convection. Heat doesn't get up to the surface. It's cold and it would freeze, and then we couldn't get out of it. And we did try a number of tests where we'd turn it on with various parameter values and other things, and unfortunately none of them were successful. So I think the final decision is that this will stay off in the Lab Sea. The oceanographers can correct me after if I'm wrong. All right, so Dave's gonna talk about the current status and how sea ice looks in the development simulations. I think, go ahead.
Sure. So apparently this is me, the inquisitive penguin. I guess we put together some diagnostics using the Cupid package, which you've heard a bit about, and I think we'll maybe go into a bit more detail about what it is tomorrow. But it's basically the CSM Unified Post-Processing and Diagnostic Package. It's replacing what we had before for CSM2, and it's still under development. So we're definitely looking for feedback on different things that we would like to include in it. So as Alice said, 271 is the longest simulation that we've got so far. But it, you know, the oceanographers will talk more about some of the issues with the Antarctic circumpolar current. And then 287 is sort of our, almost our best tuning. I'm sure that there's still more to come, but at least for now, this is kind of where we would like things to be. And then, yeah, the atmosphere is still working on tuning some things, trying to make sure that they get the ENSO they want and so forth. And so while our development, our piece of this is done, we may still have some tuning to do. So, and this is just sort of saying more about the Cupid package. There's a web link here that you can follow. It's fairly well documented now. We haven't really tested portability to other machines yet, but it does work on the NCAR machines very well. And we would definitely like other people to start helping and contributing to this package. 287 versus 271, in terms of like a lot of the, you know, standard metrics, it actually looks like these two runs are fairly close together. Oh, sure, yeah, there's my mouse there. You see the Northern Hemisphere sort of climatological seasonal cycle near the end of the runs in each, and you can barely tell the difference between the blue and the red curve. They're very, very similar. I've put on here the black curve, which is the CDR, which we heard about this morning. That's present day, of course, and these are pre-industrial runs. So we would expect that we should be above that somewhat. And so that when we go through the 20th century, we're going to expect some melt back on that. And then we have some fairly nice statistics of comparing the different runs in these box plots to sort of get an idea of the spread in the runs over time and how they compare with the CSM1 and CSM2 large ensembles. The CSM1 large ensembles in gray here and the CSM2 large ensembles in blue. And then here with volume, again, you know, the two CSM3 development runs are not really that distinguishable in terms of Arctic volume in the seasonal cycle. You can see we're at kind of the higher end of the CSM1 large ensemble in terms of volume. But so far, with the historical runs we've done, we're not that concerned about it yet. But I think we definitely feel like we should be within the sort of CSM1 spread instead of CSM2. CSM2 was too thin in present day, so it's kind of desirable to be closer to the CSM1 large ensemble. And then, you know, some additional plots that we have, we can look at the whole run length. And so this is on the left here, we have the annual mean ice area. And you can see generally, you know, there's slight variability differences between these runs over time, but in general, they look pretty good. And the reason you're seeing the CSM1 and 2 large ensembles sort of drop off is because they're historical runs, and so you should only really think about the early part of that period there. And then we have some spatial plots too to look at some of these things. So sea ice concentration, I've got on here in the pink line the 15% contour. And so as CC pointed out this morning, these runs are actually looking pretty good in terms of the Arctic extent and concentration, maybe a bit thick in terms of the thickness, but that's another thing. And then in terms of the volume, again, they were very similar, but you can see a lot larger variability in the volume. This may actually be related to some of the variations that we're seeing in the ocean too, although this is northern hemisphere, it's kind of more obvious in the southern hemisphere. But in general, the thickness pattern is kind of what we're expecting. We're getting the thickest ice over towards Canada and Greenland. And then we also have snow volume as well in these plots. And so what's kind of interesting here is that CSM1 large ensemble had a very high snow volume in the northern hemisphere. And that also, it tended to create a slightly colder climate, especially in present day, whereas the snow volume significantly reduced in these new sensitivity runs. So that's interesting in itself. The reasons why, we're not sure yet. It may be less precipitation from the atmospheric model, and it may just be differences in processes within the ice as well. Then also, as Alice highlighted, we do have wind redistribution of the snow, and that may also be contributing to this too. So then we also have tons of different metrics for different things. I've included flow size perimeter here as that's one of the key metrics that we're looking at when we're trying to think of either the machine learning method for computing this or the full flow size distribution, because this goes into the lateral melt. And you can see here the Central Arctic flow perimeters are very, very small. And that's because it's much bigger flows. There's less perimeter around the bigger flows. And then out near the edges, what's kind of interesting to me in these simulations, and maybe Letty or someone else can explain this, but there's this kind of peak in the flow perimeter, right? Sort of just before you get out to the outer ice edge, and then it drops again. So I'm kind of interested in what's going on with that process. The ice velocity plots, I will apologize. I'm still kind of struggling with these in Matplotlib, so would love to talk to anyone who's got experience with the quiver plots, because it's very, very difficult to get these. The old NCAR command language NCL did a beautiful job with these, and so I'm having a little struggle here. But that is part of our diagnostics. And then we're underneath the vectors, we're just contouring the speed. And so you can see this white area off the coast of Greenland where the velocities are just flying along. Let's see, Southern Hemisphere. This is where we see a little bit of more of a difference between the two simulations. And I think overall the seasonal cycle is fairly comparable and pretty good. We are worried a bit because we're really low in summer. So the black line here, which you can barely see, is the present day OBS for the Southern Hemisphere, and we're below that. So in a pre-industrial context. So the only problem is we don't know how to fix that in the summer. So thoughts on that would be great too. In the winter, we're a little bit higher than the OBS. And that's okay. It's a pre-industrial run. And so the idea is over the 20th century, we would expect some decline in that. However, I will say, I think we have the time series. There's a lot of variability in the Southern Hemisphere sea ice too. So we're just, that climatological plot was over 30 years. And so I think what we're just seeing here is Southern Ocean variability. You can see here the 287 run, near the end of it, it kind of pops up, differently. And some of this variability is probably related to the Antarctic circumpolar current as well. And you can see this similar sort of thing in the ice volume and the snow volume too, that variability over different, multi-decadal variability and so forth. And there's a little hint of this sort of oscillation going on here, though it's not as obvious in the annual mean plots. And then similarly, we have flow size perimeter, ice velocity for the Southern Hemisphere. same sort of thing, the flow size perimeter, we're getting, you know, larger values in the interior of the pack, and then smaller perimeters near the outside of the pack. So, and all the major features we're expecting in the velocity plots are, you know, we're getting that sort of related to the ACC transport. We're getting that same sort of transport in the ice as well. So I think that's it. We'll hand it over to the oceanographers now.
Diamond is online now, so we're going to have her just quickly present, and then we'll hand it over to the oceanographers. All right. Are you able to share your screen, Diamond?
Yeah, well,
I can do it too, and we can hear you.
oh, okay. Yeah, if you don't mind doing it for me, just so that I don't want to take up too much of your time. We, the authors of this EOS article that I'll throw in the chat, Laura, Mari, myself, and James, and Julie Maldonado from Lycan, we wrote this article in EOS that came out a couple months ago. The title of our EOS article is Environmental Hazard Impact Metrics That Matter. Basically just trying to make a pitch to our scientific community that, you know, our disciplines and the way that we communicate our science to each other is very limiting, where we don't reach broader audiences. We don't reach communities, people who live in these areas that we do our science in. And so our CESM workshop cross-working group session is called Storytelling to Craft Climate Science Tools for Communities. Just wanted to throw out to everyone, if you could keep an eye out for this session, and please join us if you can. And yeah, basically that's it. We just want to keep having this conversation with our fellow scientists, and trying to figure out how we can reach more people who will be and are currently impacted by the science that we do. So these are just different iterations of slides that we were trying to put together to engage you folks. So yeah.
All right. Thank you,
That's all.
Diamond.
Thanks, Alice. I'm so sorry.
Happens.
Thank you.
Okay, now moving to the CSM3 ocean model status. I think we're running out, we're kind of behind the schedule, but we have discussion after, so it's okay that we take our time here. Since Alice mentioned that there were over 300 couple runs so far, I decided to also throw how many ocean-only runs we have done in 2025 alone, and it was almost one every other day, so it was 159. There's actually more because Ian likes to do A, B, C, G. I think it was way more than 159. So this table is summarizing the key differences between our old model, POP2, and then the GFGL MOM6 version and the CSM3 MOM6 version. I'm not going to go through all the details. It will be in the slides that will be shared with everyone for your reference later. What we will touch upon today are what's highlighted in blue. So these are kind of major changes that were done over the last year. So there's changes with APP and the FPMix and Stokes-Most package, and then the adoption of the Bodner scheme, as Alice already indicated, with wave coupling, which is new. I'll mention briefly. And then there's the two backscatter schemes that Ian have developed, and Ian will talk about these two as well. Okay, before we jump into the physics changes, as I was preparing this talk, I decided to look at 287, our best fully coupled simulation, and then I compared against the GKs, just in terms, just to make the point that we have too much precipitation in the couple runs. I've shown these type of plots in the project meetings before, but I want to highlight to the broader community. So we're looking now globally, like if you integrate globally all the river runoff in the GKs in red versus, which is coming from the GRA, versus the fully coupled 286, that's the discrepancy that we see. So this is liquid runoff. Here is frozen runoff. And then in the couple run, we're separating the frozen runoff coming from land versus the frozen runoff coming from the glacier model GLC. Okay, so if you take a look at these numbers, and there's 40% more liquid runoff in the couple model globally, and 80% more frozen runoff compared to the GRA. So that we do a pretty good job at constraining rest-on, but the hydrological cycle is very different between G and D cases. Of course, we're doing salinity restoring in the G cases, so it doesn't play a role, but it's interesting to see, and I think we should try to understand what's going on and have the two type of runs be more similar in terms of the P minus E budget. If I was looking globally, you can also look at the lab C only, the same type of thing, and it's 24 more liquid runoff in couple runs and 500% more frozen runoff. And remember, frozen runoff, when we add in the ocean, there's latent heat associated with melting that. So it's not just the mass addition, there's a big contribution in the heat budget as well. So no wonder why our lab C freezes pretty quickly in these fully coupled cases. And then finally, this similar issue in the Southern Ocean, although it's not as bad because they balance each other. So there's way more liquid runoff in forced runs, so 500% more, which is constant, by the way. Both the frozen and liquid in the G cases are constant around Antarctica. But then we have 100% more frozen runoff, and if you look at the numbers, it kind of balances out. So they combined are not that bad. The issue might be here how we spread them, and I think if we have time, we will talk a little bit about that now towards the end of this talk. Moving to the parameterizations. So we already mentioned that we adopted the Bodmer 2023 MLE formulation, and before we were using the FFH, so the Ferrari, it's Fox Samper, Ferrari, Halberg 2010, I think. So that was using CSM2. It was using earlier versions of CSM3, and that parameterization. So the stream function on the left here is the old parameterization, the FFH. On the denominator, you have the L sub F parameter. So that is the length scale of the fronts in these mixed layer eddies, and that was prescribed. And you also had that C sub E constant. So there's like two tuning knobs that you had to prescribe. And you're using the same length for the frontal length scale globally. And Bodmer improves upon that by it's better physics. And then with that, you remove the need to prescribe the length scale, and that's kind of done prognostically for you. So it is, there's a lot of advantages in going into that scheme. So I mentioned the frontal length scale, but also in the paper, they provided a way to couple with the waves, even though that's not what was done initially in MOM6, but then Bill, Large, and I, we added the option to enhance the U star that goes in the denominator by using the Langmuir number from the wave model. So there is now a coupling with the wave model going into the MLE as well. So good reasons for switching to these Bodmer 23 schemes. And then we mentioned the lab C freeze issue. And if you look at the stream functional, we can focus on the one on the right-hand side. There is the lowercase h, so that's the boundary layer depth. There's the capital case H, which is the mixed layer depth, both of which are very deep in the Labrador Sea. So you will generate circulation. And also we have, as I mentioned, we have this bias in the precipitation, therefore the runoff. So we have very large gradient of buoyancies in polar regions in general. So therefore you're also enhancing the circulation by that. So because of that, like deep mixed layer depths, deep boundary layer depths, and large gradients, the restratification in the Labrador Sea is very strong, and that it's opposing convection, and therefore is leading to the lab C freeze. And to give you more of an idea of how that we've been trying to understand that, so we focusing on again on the Bodmer, so the right-hand side of the stream function, we can set this constant CR, which is the only knob that we have here, to 0. And here is in the couple case how the stream function looks like. So basically only the Labrador Sea, by the way. there's zero effect of this formulation, this parameterization, then elsewhere in the globe, in that case where CR is equal 0, CR is 0.01. But then we decided to, okay, let's use the same CR and now turn on in the Labrador Sea. And then you see this circulation. So it is converging in the middle of the Labrador Sea. So it's bringing fresh water into the middle of the Labrador Sea, and that's shutting off convection. But then we'll say, okay, what if we have that? And at least we can try to keep the Bodmer on everywhere. And having CR doesn't really have the string function. There's a lot of nonlinearities going on, and I think because of this gradient in buoyancy, the string function changes, but the magnitude is still strong enough. So we've reached the point that even a very small amount of submeso through Bodmer in the Labrador Sea, it is leading to freezing. If I do the same exercise on the G case, forced case, it's completely different. I can see a better response on the string function to the CR, but in the couple case, things go pretty wild. And then the two cases that CR is non-zero, they lead to lab sea freeze, and that's shown in this time series of area integrated mixed layer depth in the Labrador Sea only. And you see the freezing in the red and blue time series. Okay, so that's just what I said. So then we're very kind of constrained, we cannot turn on this parameterization in the Labrador Sea, otherwise we'll lead to freezing. Okay, so now moving on to KPP. There were a lot of changes to KPP. So we added the explicit effects of surface waves, Langmuir turbulence. And by doing that, we had to remove the implicit wave effect. So if you go into CSM2, there's an assumption of what the waves are doing, hard-coded into the KPP. So when we explicitly added the waves, we had to remove this implicit wave effect. And then we had to rebalance by compensating errors. And then we also added this cross-graded non-local momentum flux. It's called the FP mix. And both of these topics were covered by Bill Lart's 2024 OMWG talk. I put a link here. And he is the best person to describe these things. However, over the last year, we made a change into how the boundary layer calculation occurs. So before, the original KPP uses the Richardson number-based method to estimate the boundary layer depth. And then we had some pretty large biases in the equatorial thermocline. And then Bill decided to try a energy-based or the entrainment rule depth of his 2021 paper in conjunction with the original KPP Richardson number-based. So it will use the entrainment rule if the surface non-local buoyancy flux is negative. Otherwise, we'll use the old Richardson number-based. So that's what we have right now. And just to give you a sense of how that improved the model, here is using the old method for boundary depth calculations. So we're looking at temperature bias at 75 meters and focus on the equatorial regions. You have a very large bias in temperature. So this is a model minus the World Ocean Atlas. And then when we switch to the new method, which combines both entrainment rule and Richardson number, we were able to improve the equatorial part in particular. There were some detrimentals elsewhere, but clearly improves the equatorial part significantly. So that was the key factor for deciding to go to this combined way of computing boundary layer depth. Okay, now I'll hand it to Ian. He will talk through the rest of the changes.
All right, thanks, Gustavo. Yeah, I'll just use the mouse. So a few other things we've added in the last year. One of them is this stochastic backscatter scheme called GME. GME was a scheme that Scott Bachman developed when he was here, and then I came along afterwards and made it stochastic. The idea is that the Jen-McWilliams parameterization removes potential energy from the resolved scales by slumping isopycnals. It moves light water over dense water. And that energy that's removed sort of goes away. I mean, it goes into a subgrid scale energy budget, but theoretically, some of that should probably get converted to kinetic energy and go back into the model's resolved velocity field. So the backscatter scheme here takes some fraction of this energy that's removed by GM and puts it back into kinetic energy. And it has several effects. The main effect, which was the intended effect, was to improve the variability. So I've got sea surface temperature, standard deviation, temporal standard deviation up here from a daily observational product. And this was the bias in that quantity without the backscatter. And then on the right, these are just different tunings of the backscatter. This is the change in the simulation with backscatter compared to the control. So we want the colors to be opposite. And indeed they are in most of the places. They are reducing the bias. They don't remove it fully. We're still deficient in variability, but they are significantly improving that. One of the things, so that's in a G case on the right. When we tried this in a B case, a coupled case this summer, it had a big impact on the southern hemisphere sea ice area, and it improved a bias there. So the blue run does not have this backscatter, and the red run does. Brought the area down, and the ice team liked that, so we decided to keep it on. That's one of the backscatters. There's another backscatter that is turned on in the model, and it is, I have actually a talk about it at 350 in the ocean model group, so I'll say more about it later today. It is a different kind of backscatter. It represents a different process. We have a biharmonic momentum mixing, a biharmonic viscosity in the model that removes energy, and that's unphysical. So this backscatter scheme puts some of that energy back in, the energy that's removed by the biharmonic viscosity. And it does it in a different way. It's not stochastic. And it just so happens that these two backscatter schemes tend to operate in different parts of the ocean. This one is acting mainly in the tropics. The other one on the previous slide is mainly acting in the extratropics. And one of the big effects of this scheme is in the zonal flow in the tropics, in particular in the Pacific. So I've got here a meridional section of zonal flow. This is observations. This is CESM2, CESM3 without the backscatter, and CESM3 with the backscatter. You've got the equatorial undercurrent is kind of the blob in the middle. And here in the obs, you can see there's a deep countercurrent. And then on the flanks, north and south of the equator, you get these jets, which have various names, including Tsuchiya jets, named after one of the people to first observe them. And in old CESM2, CESM3 without backscatter, you don't see those things, but you do when you turn on the backscatter. And as was pointed out by Keith Lindsay when we first saw this, this could have an effect on the ocean biogeochemistry, and in fact it does. It reduces a bias in the extent of the oxygen minimum zones in the eastern tropical Pacific, which has knock-on effects on other aspects of the biogeochemistry. So this is, the blue line here is RMSE in one of the nitrate. And without the backscatter, it's quite high, and with the backscatter, it goes way down. Same thing with oxygen, not as big of a change, but still an improvement. So that is currently on by default. There are some detrimental side effects of this, which I'll talk about in my talk this afternoon. So how does the equatorial undercurrent look in our current configuration? Here's observations. So this is a zonal section now across the equator of zonal flow. You see the equatorial undercurrent here, a little bit sloping. This is our current development run. You can see we're a little bit too fat vertically, and we extend maybe a little bit too far to the west. We have here CESM2 results on a different color scale, but the conclusion is actually they're kind of similar. So the equatorial undercurrent in CESM2 and our current CESM3 are pretty similar. Okay. We're currently dealing with a problem with the Antarctic circumpolar current, which was alluded to previously. So here I'm showing time series of, actually, I mean, Gustavo made this plot. I'm just talking about it. We're showing time series of the transport through Drake Passage, volume transport. 271 is this long run. And you can see the transport starts in the, where am I going here? Transport starts in the gray, which is the sort of observational range, And then it drops way, way down, 110 sphere drops, which is way too low. And then it recovers, goes back up, and then it goes way back down on a very slow time scale. And we were not expecting to see this. So we tried tuning a lot of things. This spaghetti is all just different tunings that we've tried. Our best one is this line here, the kind of light gray line, that's 287. We are doing some more tuning ongoing, hoping to improve this further. It does seem to be associated with convection, deep convection in the Ross and Weddell seas, and in particular, a lack of deep convection in the Ross and Weddell seas. So in those seas, the stratification with respect to temperature is inverted, so it's warmer at depth and colder at the surface. The density stratification is dominated by salinity. That's why the warm anomalies don't just rise up on their own, because it's warm and salty at depth. And if there's no deep convection to release those heat anomalies, they just build up, and then the temperature gradient and thus the density gradient meridionally across the ACC decays. You get less of a density gradient and therefore less transport through geostrophy. And so when these anomalies at depth build up, the ACC goes down. When a deep convection event wipes out the anomaly, the ACC recovers, and that's giving us some insight, and we have some hypotheses as to how to fix this, but that's ongoing. Okay, I'm now coming back. So there is I'm going to talk about the deep circulation here. This is meridional overturning circulation, global, not Atlantic. And on the right is CESM2, on the left is CESM3. We had a very weak, deep cell here in CESM2, which was pretty detrimental to the ocean biogeochemistry. We are doing better in CESM3 right now, still pretty far from OBS, still pretty weak. So that's related to Antarctic bottom water formation. Happens down here, comes down and drives an overturning cell here. We also think that the strength of this is related to the ACC oscillations that we're dealing with. So we're hopeful that some of our tuning here with the ACC oscillations will also help improve this deep overturning cell. And then I alluded earlier with the Leith backscatter, Leith E backscatter, I alluded to some detrimental effects. And you can see on this slide, one of those detrimental effects, really the main detrimental effect, which is that there's a very large and spurious upwelling at the equator. There's a very strong overturning cell right here, which we don't see in observations or high-res models. So that is where we are. Summary. Mixed layer eddies. We used to use FFH in CESM2. We're switching to Bodner, but we've got it turned off in the Lab C. Okay. Lots of changes to the vertical mixing scheme, KPP, a lot of connections to waves, which is great. Also, Bodner is connected to waves. We have this stochastic backscatter for the mesoscale parameterization. We have another backscatter, which is not stochastic, which is improving BGC. And then in progress, we're tuning to try and improve ACC and also improve the bottom cell. And that's it. We'll move to discussion next. I'm going to invite my co-chair, my fellow co-chairs to come up for the discussion. And for the discussion, I believe we're going to use the room mics. So I'm going to stop using this one.
Just like feeder topics, but anything else means if you have something else you want to talk about. So I guess I'd say start if there are questions about CSM3 release or the components or CMIP 7 or whatever. Anyone else who wants to start the conversation? Don't be shy. I'm sure people.
One question just to start us off. I don't know much about the Labrador Sea issue, but have other modelling groups had that before, and how common has that been, and what approaches have they used to try and get rid of it?
I think it's been an issue for CESM since before I came here. I don't know if someone else can. Peter, how long has it been an issue for you this?
Since we started.
Okay, and I know other groups have had issues with it too. I think a lot of it has to do with like it's this kind of funny basin, and when you're using low resolution models, you can't perform lateral gradients do you need? I think E3SM,
Also had issues with lab C.
yeah, E3SM had issues. I think they solved it with resolution.
It is looking a lot better in our recent version 3 release. I'm not sure if I know the answer of what exactly solved it, but yeah, we've had a lot of updates. And so yes, it's been pretty persistent issue across a lot of models, I think.
Our regions, most models.
I was just going to, it existed in CSM2 as well. We couldn't, there is no silver bullet. I mean, in this case, it's being addressed through the submesoscale mixing scheme. In CSM2, what we ended up doing is essentially we ran 3 ensemble members of the same configuration. 2 of them froze, 1 didn't, and we continued with that one that didn't. So, and one difference is that in CSM2, whatever we did, if a case did not freeze until year 106, everything was okay. In this case, it's not the case.
I was gonna say too, can we get anyone online, if they raise their hands or chat, we'll get the configuration difference so we can see it.
I just want to add on the lab C, that we never had any issue with high resolution. So if there is one silver bullet is that if you run high resolution, you don't have that issue. And ESM as well.
Can ESM also?
I think the atmosphere changed resolution too, though, so.
I mean, it's sort of implied by Gustavo's talk, but do we expect the precipitation to change dramatically in the upcoming development runs?
Against CSM2.
No, in CSM3, right? If I understood right, you were showing that there's too much precip happening.
Yeah.
Is that something that might change?
Don't expect it. Yeah, this time, I don't think we solved the problem.
We could pipe it to the Amazon. It would be happy, but-
Yeah, the short answer is no, the precipitation, no, but Bill Lipscomb's here and they're doing these, fully interactive Greenland ice sheet runs. So at least we won't be getting the frozen runoff from Greenland as much in the fully interactive Greenland runs. And I looked at one of those that Gunter had done and it does look pretty promising in terms of the fresh water getting into the lab scene, so.
Have you guys run no waves plus waves to look at what the impact of the wave ocean coupling is in CES?
Not recently.
It's pretty deeply embedded, so it's kind of hard to just flip a switch and turn it off at this point. You have to reconfigure the whole vertical mixing scheme to take
Yeah.
account of the fact that it's not using waves anymore.
Yeah.
So we haven't done that.
On this coordinated experiments, it would be nice, once we kind of have a final version,
Yeah.
to have at least some PI control for some period where we do try to turn it off just to see like what are the ocean impacts, what are the ice impacts. Maybe we freeze the lab sea immediately and that's the impact. I don't know.
Well, because when I did that experiment, I did see a big increase in ice in the lab, see where the wave ice impacts kind of negated it. I was wondering if you guys got sort of similar impacts with the wave coupling in the ocean versus not.
So the FSG came in very recently.
Yeah.
It was
Right, right.
Like a month and a half or
Right.
so ago. Before we had Bodner off, and most of the runs, I would say 90% of them would not freeze. And there were, and I think it's related to the initial condition. We always start from initial conditions from a G case, and then I think I used a initial condition early in the GRA cycle. That was the case that Dave then ran for longer with FSG, which freeze and then unfroze.
Yeah.
But I don't know, I would say that 90% of the runs that we did, once we turned off Bodler in the Labrador Sea, did not freeze.
Right. We did have this sort of interim thing we tried where we had only the one-way coupling, so we had wave attenuation under the ice. And in those runs, remember, it was freezing the lab sea quite a lot too. And so we were toying with the idea of having wave attenuation only when latitude was negative. And fortunately,
that was when I got the idea to turn on the full FSD. So now we have wave attenuation everywhere, so.
Yeah, no, I guess I was just interested in the impact of the wave mixing stuff on the whole system. But
Yeah.
it's a hard one to isolate for you. Yeah.
We'll have to return it.
Yeah.
Yeah.
Yeah, so basically, just a related thought, so right, there seem to be, once you have the wave ice coupling, you have now linear impact under the ice. Then you just showed your ACC issue seems to be not enough convection, but this might impact that. So there's like several balances now that can compensate or create the issue. And I think that it might be a weird sticky point, right? There's also like all this other surface forcing, catalytic winds that can affect it and so on, right? So yeah, I think maybe you, as I said, have somehow figuring out a coordinate set around that probably. I don't really know how to sort it out.
Yeah, it's possible that by attenuating the waves under the southern hemisphere ice, we improve the physics, but now we have less mixing, and so we have less release of the heat anomalies, and now all of a sudden we have an ACC problem, which is a classic compensating errors thing.
Yeah.
So we want to leave the flow size distribution and wave attenuation on, and then try to tune other things to fix the ACC.
One thing that is up for grabs, if you ask me, is what should be the wind energy input into the surface waves in the presence of sea ice. Currently, it's proportional to the sea ice concentration. There's no basis for that scientifically. So that's something you could tune. You could make it nonlinear, like and increase the wave energy. And if you want more energy in the waves, increase the wave energy input in the presence of sea ice. And
How's that done? So like that's the stress calculation where you split up between stress goes in the wind stress goes in the ocean and then the waves, but I actually don't know what CSM does. There's no flow. Right. So all the wind stress goes in the ocean and you also drive waves. I guess so.
Yes, is the first scheme that Eric showed before they modified. So that was the original.
Oh yeah, because the use of implementation.
If I can jump in, I had a question for Gustavo on the Lab C stuff again. The iceberg input you showed was pretty striking in the coupled model, and it seemed way too high. I was curious, where is that bias originating from? Is that like, do you have a balance with land precip and iceberg input into the ocean, I assume? So is it too much snowfall over Greenland that's causing that? Or are the icebergs advecting erroneously into the Lab C preferentially? And then a follow-up, have you done any sensitivity tests where you either turn the icebergs off or force them to melt quickly or something just to reduce the freshwater input into the Lab C? And did that help this issue?
Maybe we don't have an iceberg model. So what we do is the same way we do with rivers, we just spread the frozen runoff using a specified radius and a decay for that spreading. So in a way, like it's a crude way of simulating icebergs, but there's no icebergs models like in the GFGL model. And you're right, that is coming from a bias in the precipitation over Greenland, and then gets routed to the rivers and then sent to us. Yeah. Actually, the frozen runoff, it doesn't get routed to the rivers. It's just like this bucket. Once the ice reaches above 10 meters or so, I think it gets sent to the snow.
Yeah, it's a snow capping.
Snow capping, yeah.
Okay, so do you suspect if you rerouted the rivers, to run into the Greenland Sea, for example, then this issue would go away?
Yeah, well, we tried, like we didn't reroute the rivers, but we changed the way we do that spreading, and that helped. So that was more than a year ago when we first saw that the Lab C was freezing rapidly. We started playing with these radius of spreading, and that was it helped initially. So by not spreading all the way in the middle of the Lab C, but keeping the liquid runoff and frozen runoff combined to the coast, which that's what nature shows. It helps avoiding the freeze, but it didn't solve the problem completely. We had to do these additional things in order to avoid the freeze.
And I will say, Mitch, in CESM2, we tried lots of stuff like all of the runoff from Greenland, we put it up into the central Arctic and stuff, and that was not successful then. So we didn't necessarily try all of those again this time, but we have tried things like that in the past.
I think Ed had his hand up. So we'll do Ed first and then in the room.
Ed?
Ed Blanchard?
Hi, can you hear me?
Yes.
Perfect. Yeah, so I wanted to ask about Dave's point that the Antarctic sea ice in the summer is bias low, and that was in a pre-industrial run, right? And so I guess two questions. One is how concerned or how much of a kind of showstopper is it if by the end, you know, when you run it with like a deck, like 20th century historical forcing, what happens if like there's no summer sea ice left by the year 2000? And you know, you could think how that could have some downstream impacts on like the Antarctic continent, right? Like making that too warm. So I'm wondering if you've thought about ways that maybe we could target that. And I was thinking about how Jen Kay, her paper a couple of years ago, when she targeted in CSM2 that the Arctic sea ice was too thin, right? And she changed a couple of parameters. We're kind of pretty much fixed Arctic sea ice without really affecting or, you know, degrading climate elsewhere. So that might be one way to go about it. And I guess the other thing is that I don't know if you had a chance to see whether that bias in Antarctic summer sea ice, if it's at all related or influenced by this really kind of, you know, large variability in the ACC.
That's a lot to unpack.
Yeah.
So I thought about it. I think a couple points, and I'm sure I'll miss things, but the seasonality, though, like it still gets really thick in winter and pretty extensive in winter. And then even in the 20th century runs, we see that the ice doesn't completely go away in summer around Antarctica. So I guess I'm not that concerned about it. I mean, it would be nice to try to bring it back. And then on your point about, you know, the less melt runs that we did in Jen's paper, that works really well for the Arctic. It does not do anything in the Southern Hemisphere. So we can't just tune that to bring up the volume in the Antarctic. So, but then your final point is maybe it's not really related, it seems, to the.
I looked at the time series.
Yeah.
The two seasons.
Yeah, it doesn't seem to be related to the ACC variability.
So Ed, bottom line is I think it's probably a bias we have to live with because we haven't been able to do anything that includes it. One thing that the oceanographers were planning to test for the ACC, I don't know if you've started this, is this spreading radius. And so they were going to bring it back closer to the coast so it's less like out over the Weddell Sea or the Ross Sea. So like maybe we'll get thicker coastal ice and it'll stay around longer, but we're not sure. But for right now, like last year this time, one of the, you know, the showstoppers was that our Antarctic sea ice in the winter was like way too extensive, and we were able to address that as Ian talked about, but we haven't, it's been like this for a long time and we haven't been able to do anything. So just like the Amazon's dead, we may have no sea ice this summer.
Well, it didn't stop some CMIP 6 models from going ahead. So
right.
I remember the Miroc model, like some models in CMIP 6 are very, like almost no Antarctic sea ice, right? Or very little. So
right.
Follow up on this.
Yeah, I was wondering if you did any runs where you buried the blowing snow parameterization?
That I haven't done.
Look at that.
Maybe increase the snow cover on the Antarctic ice. Yeah, maybe.
And see if that's causing.
Yeah.
Although if the blowing snow is compensating for far too much snowfall in the Arctic.
Yeah, I agree, but I'm also worried about, you know, overdoing it in the winter. You know, so
We can do some tests with that.
yeah, but we can test it.
Regarding the lab C,
I'm wondering what are the trade-offs you have of like turning on and off Bodner? And the second is, what are your thoughts? I know it's like a resolution thing that sometimes like the continental shelf can like constrain fluxes from the continent into the ocean. And I'm just wondering what are your thoughts about these two topics?
I think that having a parameterization where you put a mask and turn it off, particular applications, we're not happy with that. But on the other hand, that particular parameterization was not developed for a place like the Labrador Sea. It was developed using LES for the Southern Ocean, open ocean conditions. And the Labrador Sea is a completely different environment. So we can argue that it is not doing the right thing in the Labrador Sea. And that was the second question.
Like regarding resolution, because I know you cannot run at a high resolution, but I was just wondering, like, what are the effects of not having like a proper continental shelf description in terms of fluxes exchanges between like shelf and slope?
Yeah, I think, and I tried to mention earlier, in the high res, this is not a problem. In the low res, like the representation of the coastal current being confined, and then also having warm water from the North Atlantic getting into the Labrador Sea, we always have that so-called cold wall bias. You see in a couple models that you don't have enough warm water going northward, making into the Labrador Sea, for example. That is a problem with low resolution models. Yeah.
Follow-up is we're thinking about having different configurations for the coupled and uncoupled cases.
Mm-hmm.
So in the case that's ocean ice, we're just going to have Bodner on everywhere. I think one of the things that we lose when we turn Bodner off is the location where deep convection happens in the lab sea tends to be kind of in the wrong place when Bodner is off. When it's on, it shifts it more towards Greenland, which is more accurate.
The other way around.
The other way around?
Yeah.
One or the other.
Yeah.
So there are some drawbacks to doing that, but of course, in the coupled case, it's more than offset by not having the lab sea.
Right. I will just highlight, we've toyed with the idea of variable resolution in the atmosphere model, because it's pretty easy to do that. And so we have like this Arctic high resolution domain we played with in CAM. The problem is MOM and SICE are not really configured to do variable resolution at this point, but that would be another nice way to deal with this.
Dan?
Understandably, it seems like a lot of the tuning targets are based on the model mean state. I was wondering, I mean, with the notable exception of the ACC ringing and so, I was wondering if, like for instance, the stochastic backscatter could have any implications for ocean variability, given that CESM is used so much for ensembles and marine heat waves and extremes.
Yeah, so our standard diagnostic suite doesn't have SST variability in it. I do look at that from time to time on my own. The CBDP package does look at that. And so we do get, it does affect the variability. The stochastic backscatter, the other backscatter, the deterministic one, also affects the variability. There's pluses and minuses. I'm not sure if I want to say definitively if it's a benefit from the CBDP diagnostics. I will say that Kate Bowden, who's a student working with me, is investigating the impacts of this on data assimilation, ensemble data assimilation, and her talk is tomorrow. So come to that if you're interested in that.
I guess along those lines, at least in the project meetings, Adam Phillips, who frequently presents on CBDP, we haven't had too many really long runs, but there hasn't been anything that's like, this one is nuts. So, I mean, trying.
Yeah, the Leith backscatter scheme tends to reduce SST variability that you compute using monthly means, so not fast time scale, right in the tropical equatorial cold time in the Pacific, which for our other development simulations is indeed improving a bias. I mentioned this at the OMWG meeting, and somebody said, oh, it's worse, it's lower. And I went back and verified, indeed, it is lower, but it's also better.
Like I saw a hand earlier.
I was going to comment on this.
reduce precipitation over the Arctic, and just to let people know, we have tried, or the atmosphere model working group tried. And they tried, I think the source problem is too much evaporation from the oceans, kind of just generally, and then that's the way you have to try to approach it.
Now they're blaming us, I guess.
No, I don't think it's a blame with the ocean.
It's the landmark.
But when they did make some changes that reduced evaporation over the oceans, to something that seemed more realistic, and then other things just went so crazy, it was like not really viable. So it's something I think we want to pursue for the next generation model to really try to get at this problem, but it just was way too far. And so went Wacky and MJO, and everything was like, precipitation was really weird. So, yep.
Just add shortly on that point. I mean, we've been working with the folks down the hill at NOAA looking at in situ mooring-based flux observations, comparing those with the models. And even the reanalysis systems show excessive evaporation over the ocean. So there's seems to be some sort of systematic problem in the representation of atmospheric boundary layers. Think of us, you're pumping too much water vapor out of the boundary layer into the pre-troposphere. So the integrated water vapor is too high, but the boundary layer is too dry. And this seems to be a pervasive problem across models.
Right. Since we were talking about this transport of fresh water from the continental shelf into the ocean, I just thought, since we are in a coupled model, how much does this feedback of not having a continental shelf would influence the open ocean? Because you have basically water coming from continental shelf and going in some cases straight into the open ocean, and then it starts mixing, and then it could create like an evaporation bias because you have more water in there, and then you precipitate more, and then the cycle will start to roll, you know.
Yeah, but I think the issue is that the excess precipitation comes from south, the way south, and gets transported northward. So it's not that localized, that there's a local feedback going on.
Okay.
If I understood correctly.
Yeah, that's it here.
Nobody's brought this up yet, but I want to make sure that we talk about it. So the coordinated experiments analysis comment, we had some discussion this morning about wave experiments, and Aaron mentioned one about turning off waves. This spring, we have the CSL proposals again, and the procedure is going to be a little bit different this year in that, like, we still welcome proposals for experiments from anyone here, but we don't have to provide quite the level of detail to CISL. So, you know, Polar Climate Working Group will get some resources, but we do need to plan and figure out what we support in terms of like big experiments. So one question is, it's unclear if there's going to be a CSM3 large ensemble or something like that. And would people want something like that? Or, you know, so there should be still, you know, the ability for individual researchers, postdocs, research groups to do experiments, but CSM3 is more expensive, and we have limited resources in that way. And so being able to plan what we might want to put some of our resources towards, like a larger ensemble or whatever, would be helpful. So if people have comments about that, I think that would be helpful for us in terms of planning. And then same with the, like, if you have a strong opinion about anything other than the deck, you know, we must do scenario ML, whatever it was. I think knowing that, or if you have thoughts about that, that would be helpful. Because I don't think CNET has actually released all of the forcings yet for like scenario net and stuff like that. We're not behind anyone. We're just going at the pace we can.
And also on the OMIP, there was supposed to be a meeting 2 weeks ago that got canceled. So I don't know if they have any broken.
Rita is going to talk about it tomorrow, so we can discuss that thing tomorrow.
Like, how many people would like there to be a CSM3 large ensemble-ish, if possible?
Education. Wow, you've got a spare billion computer hours.
I mean, you guys didn't mention the cost of CSM3 though, right?
Yeah, that's because I don't know what it is with the new level.
Higher than CSM2, I guess.
I said it's expensive. You have to ask, it means it's too much for you. Right, so there's support for some sort of ensemble, maybe not 100 members, somewhere, you know, there's questions about what's the right amount, but some number of like, I don't know, 30 to 50 or something like that. And for people to be able to use as almost a baseline for community experiments or something else. There is support for that.
I think we talked about this last time. There was some discussion about like time period. Maybe I asked this, like, you do a large ensemble for a smaller time period.
Yeah, I mean, I think there'd be questions about how it's done. Like for the CSM1 large ensemble, it was 1920 to 2100 to help with the cost. And for CSM2, it was 1850 to 2100. Maybe it's, we run, this is just an example, like 10 experiments all the way from 1850 to 2100. And then we have smaller bursts at whatever, where you have a lot more. I think all of those are possibilities, but it sounds like people would be interested in some sort of group of ensembles to be able to compare against details pending.
Yeah, I mean, I don't know if this is quite the right forum, but I do think it'd be very interesting to do some sort of perturb parameter ensemble with, you know, there's a lot of knowledge about which tuning knobs are helpful and not helpful, but actually putting that into a set of simulations would help people figure out, you know, where do we need to focus. Right.
Yeah, and it's recorded. So.
Are there plans for the CMIP 6 forced runs?
I don't think that there are specific plans for that yet, but if there's support in the community, just like Marika led a CESM2, CMIP 5 ensemble, with people like a CESM3, CMIP 6. Try to get my numbers right here. Is that some, you know, if you had to choose ensemble versus that, what would you choose? And then there is a lot of logistics that goes into, like, we want to run CESM3 with CMIP 2. There might be some challenges with how to make the forcing happy.
So far don't seem to be as different this time, as far as I can see so far. Compared to, there was a really big difference between CMIP 4 and CMIP 5 or CMIP 5 and CMIP 6. I'd like someone else to confirm that, but that's my sense. When we switched, we didn't see like a big difference in the simulations.
Ed?
Yeah, on a similar note, I'm wondering what the thoughts are, or what to do with the biomass burn-in. Because I know Patricia and John Fasulo showed with CSM2 how what a big impact that could have, especially in high latitudes, in the Arctic. And I don't know yet what the CMIP 7 future, or like 21st century biomass burn-in scenario is going to look like. As far as I understand, the historical forcing files are going to end in 2021, which is kind of one of the peaks, or, you know, biomass burn-in in boreal regions peaks. And so I don't know how that transition is going to look like in the forcing files, but you know, I'm remembering that kind of funny feature that CSM2 had, right, as it transitioned. I think we should be aware, or at least attentive to that.
I will say, I think that there's been, like, Isla has done a lot more with getting forcings and basically like making sure everything looks reasonable so that we don't have weird transitions. I don't know that we have an answer yet, partly because we haven't decided on a scenario yet. I'm not even sure I haven't been deeply involved in the scenarios, but they're not even released yet, are they? Like, is the forcing released for the scenarios?
No.
No. So, but I think it's a good point. We can keep it in mind when we choose whatever scenario we might do to make sure that this transition is not super abrupt, and looks like, do some testing on that maybe first before we figure out how we want to transition.
We will be smoothing the biomass burning for sure.
Okay.
Either they're going to provide the data set. It's unclear what.
Well, I mean, they're aware of the situation, so I suspect that they'll take care of it.
Well, they're being a little waffly as far as I can tell, but also we're also, I think, smoothing a few more of the emissions files that had I went from smooth to high infrared variability. It might have less of an impact, but probably still aliasing onto things. So at least I've asked the team to just say, let's just make the decision to we're going to smooth everything because it's not really a realistic thing to do. So if anyone really doesn't like that idea, that hear from it, but probably it's more to go like the chemists who would care about that. We also have the capability to run with interactive biomass burning emissions, and probably not going to do that for the default, but we probably will have a configuration.
And again, I think if we have some kind of baseline set of simulations, medium ensemble, whatever we want to call it, and then you want to run a non-smooth version, you can compare. Like if that's something you're interested in, Ed, we could compare how big a difference it makes, but that might not be the default. All right. A few more minutes. Any other burning things people want to talk about? Everything the mid-afternoon.
Unintended.
Sure. Bring it. Any freezing things you want to talk about?
Alice, I don't know if this is the right moment, but I know you mentioned Cupid, right? Is still under development.
Yeah.
And I ran it myself a month or two ago, and there were definitely still a few kind of issues with it, especially for like single run, like the way it's set up by default, or at least 2 months ago, was to compare with a base case, right? So you had to kind of edit it if you just had your own run that you wanted to post-process. And then I think the ability to do like monthly and daily maybe wasn't quite there yet. It might be now, but I'm just pointing that out because there might be other users that kind of run into those issues. But I'm sure the Cupid team's kind of aware of that.
Thank you. Just thanks for letting us know and letting us know that you ran it. I think it's hard to maintain a diagnostics package that works for everyone. And like Dave and I have done a lot with what we have, but if we don't get feedback like this, then we don't know what doesn't work. And yeah, go ahead. Mike is leading Cupid stuff, so.
Yeah, so I will say that we know that the time series generation, I think that's what we're talking about, the different streams. Like that's an issue that we're working on. We're going to replace the tool that generates the time series and put in something more robust and fix the API so you can't generate time series.
Exactly, yes. So I wasn't more clear about the time series generator. Yeah.
Yeah, so that'll hopefully be changing like in the next week or so. And I guess I'm a little surprised that you can't just set the base case to none and turn off all of the baseline comparisons. That might be something that I thought we did that we never actually did. So I'll look into that. But,
Mitch?
Yeah, I was curious to hear a bit more from Ian, maybe, and Gustavo about this ACC issue. So you mentioned you had a couple of ideas for improving this, like these big swings in the ACC. What exactly are you playing with? And I think you both know that we've had a lot of these issues at GFDL as well. Very similar sort of linear ACC, sea ice, sort of centennial scale variability. This looks a bit bigger than what we typically get, I would say. But our fix has been increasing the land ice albedo over Antarctica, which increases intermittent convection in the ocean, which chews up the subsurface heat reservoir. So yeah, just curious what you have in mind and if anything's worked so far for you.
So one thing we found a bug a few days ago. We intended to set a minimum for the radial coefficient throughout the whole water column. And there is a flag that says ensure minimum is applied in whole water column, but it only assures that it is applied within the boundary layer. So the neutral diffusion part does not have a limiter in the minimum radial. So with the vertical structure, you actually can go to 0. So we're not doing enough mixing below the boundary layer, horizontal mixing, mesoscale mixing. That is our kind of, we had a few runs going, like 2 of the runs are trying to target that. So we fixed the bug and now we're playing with 2 different minimums. One is 50 megasquare per second, and one is 200, with the hope that we'll be mixing more and then avoid the buildup of heat at that. And then the second one, we briefly mentioned that we're spreading the runoff differently now. So the default is, I think, is like 250 kilometers, which a lot of freshwater and frozen runoff goes into the middle of the Weddell and Ross Gyre.
So similar to the lab C problem, it is shutting off or helping shut off convection. So we are now using a smaller radius, 100 kilometers, with the hope that that fresh water will be confined again along the circumpolar current, or no, the Antarctic circumpolar current. No, shelf. Antarctic shelf current. Thank you. One of these coastal currents, and now go into the middle of the gyre and shut off convection. So those are the 3 runs that we have going.
Also vertical mixing one, right?
Oh yeah.
Also, yeah, we also tried a bunch of things that didn't work that might be useful for you to hear. So we tried reducing the bottom drag coefficient to speed up the ACC. That had minimal effect. We tried reducing the GM coefficient, and that actually does have an effect. That actually takes you from blue to orange to gray here. So reducing the GM ready coefficient improves things, but it also has other detrimental effects. Classic one is that the SSTs get colder when you reduce the GM coefficient, and it has effects on restom. And so that's about as, we do think that if we reduce GM further, it would help that, but it would, the knock-on effects on other things are more than we can stomach. So that's as far as we can go with reducing GM. We also tried the bottom boundary layer efficiency thing that you guys changed in CM4X, and that didn't do anything to us. What else did we try?
The vertical mixing.
Yeah, we increased the background vertical mixing, and that had, that's great. That's this one. So it has a big positive impact on keeping the ACC in range, but it screws up so many other things. So we can't do that. So we're now thinking about selectively increasing the vertical mixing just around Antarctica. I'm curious, what's the mechanism? Because all we've tried is ocean tuning knobs. And you talked about the land ice albedo. What's the mechanism for that?
So, I mean, the land, it's a bit of a red herring, I think. It's basically just anything that changes the surface energy balance over the Southern Ocean. And so the effect of the land ice albedo was to cause Southern Ocean cooling, which generally destabilized the water column and just prevented those big subsurface heat buildups. We still get them, but it at least mutes them quite a bit. So I think anything that would cool off the Southern Ocean a bit, but then you tend to have positive sea ice biases. So there's a lot of a lot of negative effects that you have to kind of stomach as well. So we're constantly fighting this balance between getting enough convection and not being too cold in the Southern Ocean. So yeah, we've really struggled with this problem as well.
Well, thanks for telling us about it.
Maybe it would help with our summer sea ice bias, though.
There you go.
I think, you know, I'm kind of joking, but I'm kind of not too.
Yeah, maybe we can go back and see if the summer sea ice number looked very good, but it's been.
Well, I mean, just if we have a higher land ice albedo.
The albedo
will
specifically.
cool, you know, especially in the summer, there might, well, I mean.
How do you feel about that, Bill?
Is
There might
it,
be
is
an
it
impact.
actually land ice albedo or is it snow?
Well, I think
They-
in Mitch's case, it was the albedo over Antarctica. So it might have been a snow albedo. I don't know, Mitch, can you?
Yeah, it was the near infrared snow on glacier albedo in our model, and we made it brighter, and then that seemed to do it.
We don't have a snow on glacier type. We just have snow.
Right, you have a bead.
So we'd have to change all snow.
There might be, I mean, there's bare ice, right? I don't know what the fraction of bare ice, there's no bare ice.
We can just change the snow over Antarctica. Latitude is less than.
Just so we can take the ocean strategy of making boxes.
Latitude negative.
Another wave possibility is there is the nonlinear source term in the wave model that's multiplied by sea ice concentration, which doesn't make any sense at all. So there's stupid things in the wave model throughout all the sea ice that I don't know whether that would, you know, it's a matter of moving it, energy across the spectrum. If it would help, it might.
Yeah, maybe we should talk.
Yeah, we just didn't want to bug Wave Watch 3 developers with too many things at once, and so we never mentioned it, but it is wrong. Patently wrong.
I also want to point out it's 3, so we probably should stop and take a break, because there's only a 15-minute break. So I guess if you have other comments, come find one of us, or we'll have discussion later tomorrow as well.
Ocean is back here at 3:30. Ice is in the area. Thank you, everyone.
very specific.